move this.
Yeah, so we have two experimenters, Alice and Bob, who are in separate rooms, so they are especially at different places. They have quantum devices and they share a quantum state. So we level the quantum device, we level there are different measurement settings for the quantum device, and we level each of these settings going from 1 till n, and each setting will have k outcomes, which we level by 1 till k. So think of something like Alice chooses a measurement level which is level B, and if she performs the experiment, she will get some outcome which will be level I. And similarly, Bob he performs an experiment W, and he gets an outcome which will be level J. So because of the probabilistic nature, we have distribution Pij Pw given Pw. That means it's the joint conditional probability that Alice gets outcome I and Bob gets outcome J, provided they perform observations, perform measurements level P and W. And as you can see that if you vary over all Pw and all Ij's, then this will form an n squared k squared number, set of numbers. And what we think of that as a big table of numbers, which we usually call correlation. So what self-testing allows us that if we know this statistics or even some part of this statistics, then one can understand, in some cases at least, we can understand what the state Alice and Bob might be sharing and what measurements they might have performed on those states. So since we are working in the quantum setting, we assume here the usual tensor product model where if we have two different persons and we want to understand that together, we use the tensor product of those subsystems. So here Alice and Bob will share a state. So what we will usually talk about is a quantum strategy where that is given by a triple. The first part is a state shared by Alice and Bob, which usually lives in a finite dimensional good space in the tensor product form, because here Alice and Bob they are separated. The second part is the measurement operators for Alice, and the third part are the measurement operators for Bob. And we have these conditions on them. So for being a state, obviously you need to have a unit vector, and these operators E, some Pi and F, some Wj, they are measurement operators, so we want them to be positive definite vector sets over their respective spaces. So ABI is positive, FWJ is there positive, and if I sum over all outcomes, so I sum over I or J in case of Bob, then I should get I. That means we are bound to get some observation from the experiment. And as I talked before, here the conditional probability that one gets by using such a measurement is given by this formula, where we take the tensor product of Alice and Bob's operator, apply it in psi, and take the product of psi. So let me give you an example in the simplest case of the CHSH game. So the game is derived from an inequality between CHSH inequality. I'm recasting this in the form of a game, a two-player game, where Alice and Bob play against everything. Here, Alice and Bob get two inputs, so either they will get 0 or 1, and Bob will also get both these inputs, and they have to answer again 0 and 1 depending upon what they receive from the referee. So, and then of course there are certain rules for the game which need to be satisfied in order for them to win. So, without going into the details of the game, one can show that the maximum winning probability, if we just use classical strategies or like just classical resources, that is straightforward. So maybe I'll just write here. So if I just use the classical strategies, then I get 3/4. So 3/4 of the time they will win the game. But in the case of quantum, if they use the quantum resources, then they will win 4 number of times, which is approximately 85% of the time. And to win this, so to win with the probability 85% of all the time, they will have to use this strategy, which I will term the canonical strategy. Here, here P2 is a state shared by Alice and Bob, which is maximally entangled state. State. And the operators that Alice and Bob use, they are the poly Z and X matrices. So if you notice that I have written these matrices Z and X, they are unitary operators. But earlier I said they are the operators that one uses, they are positive semi-definite operators. So one can just break these poly matrices into an eigendecomposition and then use the projections from them as operators that I listed before. So Alice uses Z and X, and Bob uses the linear combination of Z and X. So, and if they use this strategy in particular, then we can show that they will win 85% of the time. So, in general, if you observe that, well, they are getting 25% winning probability, and suppose we just assume that they share some state and they use some strategy, then one can show that one can choose isometrics going from the space that the state lives. So for Alice, it will go from CD to actual space where these canonical ones live, then insert some space, and similarly for Bob, such that if you look at the state obtained after measuring AI tensor PJ, then that will factor as the canonical operators apply to this canonical state and insert some channel state. So in other words, like if you have any kind of strategy to win this kind of game, this is CHS game, then it has some rigidity structure that you can understand what the operators in state might be, just looking at what the maximum winning probability of the game is, of that strategy is. So this is an example of self-testing. But in real life, we don't actually see we won't actually see the exact value of the game appearing in experiments. We might see something like 0.84% of time or like that. In that case, the robust part comes handy. So where we know that, say, the quantum winning probability of the game is very close, it's epsilon close to the actual one. What can we say about the state and the measurements involved? With the robust self-testing case, one can show that actually the vector over there on the left-hand side is it's also close to the actual vector that we want to, up to some f epsilon, which where f epsilon obviously f epsilon. So this is one example of self-testing in the CHSH case. So in our case, what we do is we don't look at a game, we look at the correlation that I mentioned before. And then we try to mimic these kind of things for those set of correlations, for that correlation. So let me briefly describe how one goes around to prove these statements. The technique goes something like this. So first we associate a group with the CHSH game. So in the case of CHSH game, what we do is that we look at the poly Z and X matrices, and we look at the group generated by these Z and X matrices. So that will be a subgroup of the unitary group, and that is actually consists of 8 elements, and that is actually the diagonal group of. Right. So one gets a group out of the game. Then one shows that if you have a perfect strategy, some which we don't know about that, then that will lead to a representation of the game. So one can think of Z mapping to say A0 and X mapping to A1, which these are addices operator. Then this association gives rise to a representation of the group. And in the case of approximately perfect strategies, which are nearby perfect ones, then this leads to an approximate representation. That means that for a group representation, you need to satisfy something like f of g times h. Inverse is f of g times f of h inverse. And in the case of approximate ones, we would want that this is satisfied in some norm up to some epsilon. So that will be what we will mean by an approximate representation of a group. And this norm is usually dependent upon the state. So if we choose psi as a state, then we look at the reduced density matrix of that state. So that will give us a norm or semi-norm on the matrices, and then one can talk about these approximate representations of the group, which are given by this one.
I have a question. So this row norm is it just that F maps to an observable? You take the trace with those observables over multiply with the state row?
Yeah.
Okay.
Yeah.
Thank you.
Yeah. So this is my F, and norm is. So one uses a group, first associates a group, then talks about representations of the group in the exact case, and in the reverse case, one talks about approximate representations. And final step, which is the crucial step, is to use one key technical theorem called the Gowers-Hatami theorem to find the isometers. Remember, in the self-testing, we need isometers going from analysis space into the actual canonical space to insert something. So to get that isometry, Alice as well as Bob, one uses this theorem, where one shows that if you have an approximate representation, so that epsilon sigma representation is basically epsilon and sigma is the state concentration, then one can relate an approximate representation F with an actual representation, and then cutting down to some order. So the good thing here is that we get an isometry from the theorem, which we then stitch together to find the final statement of the surface. So this is a high-level map of how the proof goes of the of self-testing of the CHSS game. In the case of CHSS game, there are other proofs as well, but this is one technique that we wanted to use or to expand for our case. So let's go to the case that we did in our work. So any questions so far?
Yeah. So you said use Gowers-Hatami to find the isometry. Does it give you an explicit one?
Yes. So I should have the mark, but I think I will have the mark later on.
Okay.
That in this case, the isometry actually one can construct the isometry from this given data. So it's not some existing like it's not it's an existence, but one is constructive proof of getting an isometry. This will contrast to our work later on, where we have a similar kind of statement, but the isometers that we get there is not constructive, which actually hinders in getting what exactly this number should be. So here the f epsilon that is exact harmonic effects.
I have another question, if you don't mind. Is there a sense in which this bound is optimal, the square root of epsilon?
Yeah, I think so. The square root of epsilon is optimal, but I'm not sure about the constants that go with it.
All right.
But yeah,
Thank you.
So what do we do in our case? So we start with n projections which live in d cross d matrices. So and there are at least 3 of them, and they have this property that if I sum them, then I will get some scalar types identity. And I write the scalar as a, so there could be different scalars. Here I focus on those scalars which are rational numbers, so that means I can write that in terms of p over d. Okay. And furthermore, we want one more property of these projections, that the scalar and the projections have this property that whenever you have any other projection which has the same property, that is sum of two scalar times identity, then those projections can be written as identity tensor with the ones that we have in our hand. So this property is what we shall use. So in other words, this says that if you look at the representation theory of the algebra generated by these projections, then you have a unique representation of that algebra. And let us denote the set of such scalars by x by lambda sum n. So to get a hold of how these things might look concretely, so think of n vectors in n-1 dimensional space, which are vertices of regular n simplex. So for example, in R2, you can think of 3 vectors which form a triangle, an equilateral triangle, and the angle, an equilateral triangle set at the horizon. And then we look at the corresponding projections, which we take as psi I, psi star. So that will form an irreducible representation of the relation P1 summing up to Pn gives us n1 n minus 1. So in the case of so now one can actually construct these n simplices in a recursive fashion, if I remember, and then one can just multiply them as one vector times more vectors to get these matrices, and then one can show that those matrices so often they sum up to n times n over n minus 1 times n. And of course, one can check this paper later on, which talks about these kind of projections and the representation theory. So what we do next is so we have these projections P1. These are projections in D cross D projections, which sum up to some square transaction. And then we want to construct a strategy out of a quantum strategy out of these projections. So what we do is we take the maximally entangled state on D dimension. So psi is and for Alice's operator, I use the projections that I have, and then take a complement so that if I add these two, I get the identity, and then of course I take another of these things. And for bombs, I might take the same thing, but then I take the transpose. So they are taking the transpose still in the projection, so they are able to get these projections. And from here, using the formula that we saw earlier, so I think that was something. And that will give us a correlation, statistics for this strategy. And we want to understand, so given only these things, we want to understand that if I have anything else which gives me the same thing, then what can we say about these states and operators involved? So as one could have guessed that we have analogous statement that we saw in the CHSS game, that if we have any quantum strategy which induces the same correlation, then that strategy must be close to the then that strategy must be related to the actual one via isometry, or in this case must be close to the ideal quantum strategy, which is approximately close to the ideal correlation. So let me state the theorem that we have. So we start with these in projections as above, the theta ones, and whenever I have any other strategy given by this S, such that it induces our correlation P, which is close to the one that we have in hand, then the strategy S can be approximately related to the one that we have in hand via local isometry, in such a fashion that if you look at these expressions, they are exactly very similar to the ones that we had in the series. So this is what we call we have the self-testing of the correlation. Here we not only self-test the state, so we understand how the state will look like if it is close, if it yields correlations close to the one that we have in hand. So that will factor as some feed as a junk state. But also in the case of measurements, we understand how that will also look like. So for the result, we have a very similar kind of idea, but in this case, we wanted to not use the technique, but we wanted to use the technique. We wanted to use the algebraic technique because at certain places in quantum information, there are a lot of algebras. There are a lot of natural algebras that would associate with gain instead of groups. So for that matter, we wanted to recast or find an example where one can do the same kind of technique that we have in CHSH game, but with an algebra instead of a group. First, we associate a series algebra, which means that we have an abstract algebra, and it has some norm which satisfies some property. So just think of the first one as an algebra which has these relations. So just like in the case of groups, we understand some certain groups as generated by some generators, and we're saying these things might have some relations on them, like this. So similarly, in the case of this algebra, we have these generators P1 to Pn, and then we have three certain relations, like we would want that thing to sum up to identity. So in that way, we get a universal algebra with this relation, satisfying this relation. And then we show that if we have an exact strategy, then that will give an exact representation of this algebra. So instead of talking of an algebra of representations of group, we now talk about representations of the algebra. And in the reverse case, in the approximate case, we get approximate representation of this algebra. Finally, we use an analog of Gowers-Hatami. So where we have that, if we have semi-definite matrices, E1 to En, which form an approximate representation of the relation that P1 to Pn sums up to X times identity, then we can find an isometry which relates these approximate objects with the actual objects tensor with something. So in this case, I should mention that I mentioned earlier as well that the isometry that one gets is not constructed, so we don't know what it looks like. What we know is that it exists some, which also gives us so the proof technique is what gives us like what if here the approximate of epsilon, then what is the exact relation of the approximation there. So modulo these two things, we do get the existence at least that we can relate these approximate objects with exact objects under some aspect. Okay, so our initial goal was to of our work was to just understand the self-testing technique based on group representations, or how we can generalize it to algebraic objects like these ones. And out of this work, we found that one actually, in a special case, one can get a result that that was a nice title of this talk. So in particular, if we just restrict to 4 cases, so n is equals to 4 cases, that means we are looking at 4 projections which sum up to some scale identity. And actually, one can show that for each natural number, we can find 4 projections which sum up to this sequence of numbers. So instead of having just one number, we now have a sequence of numbers, and for each of those numbers in the sequence, we can find 4 projections which sum up to that number. That means one can use those projections in the way that we defined earlier to form a strategy. And as a corollary to the theorem that we proved earlier, we get that each of these strategies can be robustly self-tested from the correlations that those strategies exhibit. Now, the good thing about this case is that here the rank of the projections, they are k. So if you just take the trace and use uniqueness of representations, then one shows that the rank of these projections should be k. Where obviously k is the number coming in that sequence. That means one can self-test arbitrary higher rank projections based on just a small table of statistics that one can. Similarly, one can show that one sees that the state that we have, which is the maximally entangled state, and here the dimension is also unbounded. One can show that one gets the probability that these states, these maximally entangled states, can be self-tested from the operations that it uses. So just to mention that some of the earlier work in this case is that for quantum states, self-testing is relatively well understood. One can show that for any pure bimonite entangled state in D equals T dimension, can be self-tested from a correlation which is 3 inputs and D outputs. So here the number of inputs is constant, while the number of outputs depends upon the dimension of the state. And recently, in 2019, Fong Fu showed that that one can robustly self-test the maximally entangled state of dimension 4D minus 1, 4 times D minus 1, where D comes from an infinite set of primes and a subset of primes. And here the size of the correlation, that is roughly 100 inputs per party. So still the statistics table is pretty big to self-test these states. And based on our work, we have discovered already that for any odd dimension D, the maximally entangled state can be self-tested by just 4 inputs and 4 inputs. So that means we just have a table of 64 numbers from which one can understand what the state would be given the statistics. So I think, and I just stated this already earlier, that given any natural K, there exist 4 projections of rank K which can be mostly self-tested by correlations of 4 inputs and 2 inputs. And I think here's where I will stop. We have some time for questions.
Questions for Jitendra? I have more questions.
Sure.
Go back to the slide where you showed approximately epsilon. I think it was maybe one more. Yeah. So you wrote approximately epsilon, but should it be like square root epsilon at the bottom? Right, because you were talking about Gowers-Hatami, and that's square root epsilon, right?
Yes. So this one, yeah. So this one, here we have a more like a quantitative type of statement that given epsilon, we can find a delta. So given that we want this approximation, we can find a delta such that if something is within delta, then this should be within epsilon. But the relation between delta and epsilon is not explicit or no.
The other question I have is, so like with CHSH, you can test maximum entangled state of 2 qubits, right? And then there's a sense in which if D is a power of 2, that's equivalent to log base 2 D E-bits, right? And so you can self-test E-bits of dimension power of 2 just using a bunch of CHSH games, right?
Yeah, I think so.
And so like it's a question of like, is there an advantage? What is the advantage of doing this than that, over that, right? Because like these projections presumably are going to be a lot more complicated to implement in practice experimentally, right?
Yes.
So have you thought about this question? I mean, it's very interesting from a theoretical perspective.
Yes. So from like I don't know how these things could be implemented in practice, but for at least maybe one of the simpler cases where we have these 4 projections, one can actually just write a program to generate those projections.
Okay.
I mean, one can get exact numbers at how these projections look like.
So in principle, you can describe mathematically the experiment.
Yes. Yeah. But given these concrete objects, I don't know like how practically like what experiment should give rise to this kind of projections that we can. For example, in the simplex case, I might hazard a guess that they might appear in certain situations because of the way these frames and things appear. But in general, I am not sure how that pan out for otherwise. I think one major thing that we wanted out of this was to extend this for this class of synchronous games, which predominantly use algebras instead of groups. So we wanted some technique which can handle these things.
It's word isometry. Is that just a synonym for unitary?
No, so isometry is goes from a smaller dimension to a higher dimension space. But if you implement that both of these dimensions are the same, then you get a unit.
implement isometry by tensoring in a pure state and so, and then doing unitary in the larger space.
Yeah.
All right, I do have more questions since we have more time. Does anyone on Zoom have questions? No Zoom questions. So is side jump, do you know anything about, is it just completely useless? Like, do you know if it's a product state? Does it have any entanglement? Or is it just like it's not the thing you're trying to test?
Yeah, in some cases, we do get, let me recall, yeah, in most cases, I think the junk state is a product state. And I think it also appears product in our case, but I don't know exactly. But for other part, we have if that junk space, if that junk state is of use. Yeah, I don't know that. I would think that maybe something more like so the way I understand is that one can basically find basis of this of spaces where one can rearrange those things in a particular way, so that one can just look at one block and say that, well, this is exactly canonical object that we're looking for, and we don't care about the rest. But then I don't know the rest of things.
So another question is, Ryan at Tulane is doing experiments with like continuous variable states. And do you know of any work on like self-test? Like it'd be very interesting, I think, to self-test the two-mode squeeze vacuum resource state. That's like a resource for continuous variable teleportation. Is there any work on that topic?
I don't have any idea about that. Okay. I would. So a lot of these things come from either you will see maximum violation of some canonic quality, or like as it like maximum winning probability of some game,
yeah,
or like that, or something which gives you some rise to some unique representation theory kind of that thing. I'm not sure about if that phenomena. I'm not aware of any phenomena which in dimensional which uses this thing. So I don't know if any based on I think that we should do this.
And related to this, I mean, it's great that you can get the requirements for the experiment down quite a bit. Are you working on trying to generalize this to arbitrary pure states? Because then that, the two-mode squeeze vacuum.
No, I am not working in that direction. The last time we talked about this thing, I talked about this problem of finding a gain instead of correlation, which might help. Same kind of thing. So I think you have some idea of how to get that gain. But instead of a usual game where one has the root function is either 0 or 1, I consider something like -1. So it's like free-valued function. It's a more general function, but is some direction towards that. Like that can be suggested based on the same technique.
All right. Well, we should probably have the next speaker set up. Let's thank Jitendra again.
So, do you want to use the same laptop or?
Sure.